It's a very good day to you all, and I do welcome you to the revision of the Industrial Electronics N5 April 2024 paper. Right, so without wasting much of the time, I'll quickly go into the questions and I will skip the instructions for the sake of progress and time, but I do advise you when you're in the exam to go through them in order to understand them, okay? So I'll just go straight into the questions. So the question number one read, with the aid of a neat labeled RC integrated diagram, indicate this type of filter, passive filter, right? So by the way, that's a low passive filter. So I will just quickly draw the diagram here, how it's supposed to look like. Okay, then we have our resistor connected in series. Then we have our capacitor connected in parallel, right? And then this marks the VC on this side, right? So of course, there is our diagram with the VC on this side, and we have the VS on this other side here, right? So we label this one R, we label this one C. So that marks our low pass filter, right? There we are. That's our diagram. And as a matter of fact, it's quite good to know why is the capacitor has to be connected in parallel, because that's indeed how it has to become a low passive filter. So we actually connect it in parallel the way it is, so that it manages, or it will be able to block AC and pass DC when it's connected in parallel like that. Right. So let's quickly go to the question 1.2. 1.2 says, choose the correct word or words from those given in brackets. Write only the words or a word next to the question number in the answer book. In an RC integrated circuit, the Mach period of the applied square wave is either greater or smaller than the RC constant. That's actually greater than the RC time constant, okay? Then 1.2, square waves, sine waves, that's square wave. Square waves indicate the presence as well as the type of error during the testing of the electronic circuit. So the square waves actually do that, right? So let's quickly go again to question 1.3. So 1.3 is saying the voltage phasor diagram of a series RLC circuit has the following values. So these are the values we have been given. And they are saying, okay, of course, VL has been given there 242.5 angle of 38.32 volts, and VC, VRIT, and VT have been given. Now, the question is saying, number one, draw the phasor diagram. That's 1.3.1 there. So let's quickly draw the phasor diagram from the given information. This is how it has to come out. So I will try to indicate it here clearly. Right, so we draw it in this way. There it is. Right, then we indicate, right, this marks our VT, the supply voltage, and we've been given there, they say it is 100 angle of 0 degree volts, right? And then we have VR, we indicate it here, right? And VR is supposed to be that's 61. We've been given there a 0.8 angle of negative 51.868. That's the reason why we have to indicate, of course, it in this way, and we indicate the angle. That's 51.68 here, right? Then this marks VC here with 164 point angle of, right? That's 164 angle of negative 141.68 volts, right? Then this marks VL at this point, and the VL in this case, it's we have been given as 242. That's 242, right? Angle or 0.5 angle of that's 338, 38.32. And by the way, we can as well indicate it here as 38.32, right, degrees. Then we complete our diagram, right? There we are with our dotted lines. Then there we go again, forming more or less a parallelogram, right? There is our diagram. Pardon, mine is a little bit poor, but it has to come out exactly like that, right? Forming a parallelogram there in between, right? There is our diagram, the way it has come out. All right. Let's quickly go to the next question. The next question was saying, calculate the reactance of the coil. By the way, I would want us to understand that this information is being taken from an RLC circuit. This is how our circuit actually looks like with our supply. Of course, no one is asking this. I'm just mentioning it for the sake of emphasis and for clarity to say we do have 100 volts, of course, here. There it is. Then, of course, we happen to have VR here, and we have also VL in this case, it's here. And then lastly, we have VC. They are the voltages that we have been given, VR, VL, and VC. Right, those are the voltages we have been given. Of course, I will not label it for the sake of progress and time, but I will quickly go now to calculate the reactance of the coil. Where are we going to get it from? We will get it from the understanding that, right, number one, if the resistor, the inductor, and the capacitor are connected in series the way they are, it means the supply voltage is still going to be the same throughout. So the supply voltage that we have actually been given here is in what were we told, that the supply IT is 5.15. So we do have the supply voltage. So we should know from the diagram that I'm trying to bring out here so that I explain using it, the supply current IT is actually the same throughout for our components, resistor, the inductor, and the capacitor. They're going to experience the same IT, the same supply current. In other words, I'm saying IT is equal to IR is equal to IL is equal to IC. It's one and the same thing, right? So how do we calculate? Let's start with the reactance of the coil XL therefore shall be equal to, right? I'm just going to create a space here quickly, right? So XL, right, is equal to VL, of course, over IL apparently, which is also equal to IT because of the diagram that I was trying to bring out there. So we simply say 242.5, that marks our VL, angle of 38.32, divide that by 5.15, angle of negative 51.68, and that will give us 49.029, angle of 90 ohms, right? There is our XL. We have calculated XL. Let's quickly go to the next question. It is saying calculate the capacitive or the reactance of the capacitor, right? That's the capacitive reactance. So it's going to be given by what? XC is equal to VC over IC. But remember, they are in series, so IC is equal to IL is equal to IR is equal to IT. So therefore, we can simply say VC, the one we have been given, 164 angle of negative 141.68. Divide that by 5.15, angle of negative 51.68. Right, so that will give us, right, dividing, remember, we have to divide this 164 divided by 5.15. That will give us 31.85845, right? Angle of, we are subtracting now the angles there, we get negative 51, negative 141.68 minus negative 51.68. That will give us negative 90. Calculating that, subtracting, of course, we get negative 90 ohms. That marks our XC. Lastly, the resistance of the resistor. That's R is equal to VR again over IR, but apparently IR is equal to IT, so we can still use the same IT. So 61.8 angle of negative 51.68 divide by, this is the voltage of the resistor apparently, and 5.15 angle of negative 51.68, and that will give us again 61.8 divided by 5.15. We are going to get a 12 angle of, right, minus 51.68 minus 51.68. Obviously, that will give us a 0. So that marks our resistance. We have answered this part of the question. Right, let's quickly go to the next question. Our next question was saying, calculate, okay, we can go now to question number 2, right? So quickly, I'm going to question number 2, and question number 2 is saying, right, okay, the power supply of a Samsung TV uses a pi type filter with an input DC voltage of 18 volts across the first capacitor C1. The filter inductor has an inductance of 5 henries and a wire resistance of 20 ohms. So the question is now saying calculate the output DC voltage at a load current of 50 milliamperes. Right, that's our question there. Right, just out of interest, I will quickly indicate the diagram how it looks like here, so that we can understand clearly why performing the calculation that we have to calculate. Right, number one, this is our first capacitor C1. It's here. Okay, let me just quickly draw it first. Then I quickly label it. Right, there we go. That is our capacitor C2. Right, they marks our output. They marks our output on this side. Right, and then of course we have our input, of course, remembering that the filter circuit is interconnected with the rectifier circuit. So we expect the rectifier circuit to be, of course, in this side, right? Now, what do we have? We have capacitor C1 here, capacitor C2 here. We have the resistor R and L, the inductor, right? Of course, having been given as 5 henries with 20 ohm resistor here, right? VDC is this at this capacitor C1. We have been told that VDC is 18 volts, the DC voltage of the first capacity. That's 18 volts. We have it at this point, right? Then what the question is saying, calculate the output DC voltage. The output DC voltage is the VDC referred, the one we find here. There it is. That's our VDC referred at the output. Apparently, this is where our output is, and that marks our capacitor C2. Right. So we are calculating VDC referred. So in calculating VDC referred, considering the information that we have, it means we can use the formula checking on the data sheet, VDC minus IDC times what? Times R1. We can use this formula here. Therefore, we can just substitute the values that we are having. VDC, we do have it. That's 18 there. Minus IDC, we have been given as in 50 times 10 to the power of negative 3 milliamperes. Right, we have been given our load current. Then multiply by R1, which is 20. Right. So directly, what is that going to give us? Punching that on the calculator, that will give us 17 volts. So we do have our VDC referred. Right. So without wasting much of the time, let's quickly go to the next question. So I just drew the diagram there to make it clear. So how are we calculating? Explain the reason why the capacitors in the filter circuit of the power supply are connected in parallel and not in series with the load. So I was indicating, I did try to mention that on the low pass filter circuit there, to say why are we connecting the capacitor, of course, in parallel. So it is for the same reason. It is connected in parallel in order to block the AC signal and allow a DC signal to pass through or to pass. So we simply say it blocks AC signal and it passes DC signal. That's why it is connected in what? In parallel. Right, let's quickly go to 2.3. We've answered 2.2. calculate the drop in the output voltage if a power supply of 25 volts is connected, a no load voltage has a voltage regulation of 8% as soon as it is connected to the load. So the question is saying calculate the drop in the output voltage, right? By the way, we have to understand that when we are calculating the voltage regulation, the percentage voltage regulation, because that's exactly what the question here wants us to use the formula for the percentage. How in the first place do we calculate that percentage voltage regulation that we have been given? Right, the percentage voltage regulation is given by V no load minus V full load over V full load, because by definition, it is the difference of the full load voltage to no load voltage with respect to the full load voltage. So that's where this formula here is coming from. So substituting the values that we do have, we can therefore safely say 8% is equal to V no load 25 minus V full load over V full load, because as it stands right now, we are calculating the V full load. So manipulating the formula to make it the subject of the formula, 8% of course is 0.08 because it's percent is divided by 100. So multiply, of course, cross multiplying them multiplied by V full load is equal to 25 minus V full load, right? So making V full load the subject, it means we can end up having 0.08 V full load plus V full load is equal to 25. Then, of course, factoring out V full load there, we end up having, or even adding them, we end up having 1.08 V full load. Then we can therefore divide. So 0.01 plus 1, that is giving us 1.08 V full load is equal to 25. It's one and the same thing. Then we can now divide by 1.08 divide by 1.08. That's V full load, therefore shall give us 25 divided by 1.08. That's 23.148 volts. There we go. That marks our V full load. We are taking this from the formula for calculating percentage voltage regulation on power supply voltage regulation, on voltage regulation in power supplies. That's very important, again, to take note of that. Right, so let's quickly go to the next question. Right, the next question here is saying, that's mark 2.4. Draw a neat labeled circuit diagram of a shunt voltage regulator and briefly describe its operation. Right, so we want to quickly draw it. Let me quickly draw it here. Right. Okay, right. Number one, we are having R here, the resistor at this point. Then we have our Zener diode connected at this point. Right, there we are with our Zener. Right, and then it's interconnected to our NPN transistor, the bipolar junction transistor here. Right, there we are. There we are. Right, I'm indicating it at this point. And then we go. Then, of course, there we are. With now, we go to our load resistor RL at this point. Right. Right. So we want to label it. That's our transistor here. We are saying this is our NPN. By the way, the NPN is the most commonly used transistor. It is the most widely used transistor. So we do have RL, the load resistor, V out. We are having it here as well. So here we are having two voltages. Here we have VBE. This is marking VBE. And then, of course, this is marking VZ, the Zener voltage. We are having it at this point. Right. Then we have, of course, our Zener diode DZ. Then we have our current limiting resistor here, right? And then, of course, this is marking the supply, right? So that marks our diagram, how it has to be, right? Then, of course, this must be accompanied by a description, the explanation, because the question is saying, with the aid of the diagram, quickly describe briefly describe the operation of this circuit. So this is what we have now to say. We are saying the value of the Zener diode is selected. So we are saying the value of the Zener diode is selected such that the bias VBE of the transistor T1, which is our transistor, this one, is low enough to keep the transistor in an unsaturated condition, right? If the supply voltage increases, the Zener voltage, which is this one, will remain constant, but the bias VBE will increase. Then this causes the transistor to be driven to greater saturation in order to let the collector voltage drop, right? Then the full, the 4 compensates, which means that drop that has occurred, it compensates for the increase in supply voltage, and in this way the output voltage is stabilized, which means our V out can be stabilized because of that. That's how regulation has to be maintained. Remember, regulation is the voltage stability as a matter of fact, right? So that's the operation of this circuit diagram, right? So let's quickly go to the next question, right? Our next question is question number 3. Question number 3 on transistor amplifiers, right? Right. The question is saying, briefly describe the function of the following components in the common emitter amplifier used on the communication systems, right? Starting with number 1, 3.1.1, the voltage divider, RB1 and RB2, right? These are the voltage dividers. What are they doing? They are supplying voltage to the junctions of the transistor. So they simply supply voltage to the junctions of the transistor. That's the purpose that they are serving there. Then number 2, the input capacitor, right? The input capacitor CB, right? This one is connected in series on our common emitter amplifier circuit. If you look closely on the common emitter amplifier circuit, it's connected in series, right? It takes us back again to the same understanding we've gathered that we were having a capacitor connected in parallel there, and we said it was blocking AC to allow DC to pass. Now this one, when it's connected in series, now it's now a high pass filter, which means it is now blocking DC signal while AC signal is passing or is passed, which means what it is simply doing, it is blocking DC signal to allow AC to pass. That's what it is doing. So now it's acting like a high pass filter circuit, okay? Let's quickly go to 3.2. Right, 3.2 is saying the following values of a fixed bias voltage amplifier without thermal components are known, okay? Positive VCC with 20 volts, IC 14 milliamperes, RC 1 kilo ohm, RB 8 kilo ohm, VBE 0.7 volts. Calculate the following values. Number 1, the collector emitter voltage. That's the one we want to calculate. That's 3.2.1 VCE, right? So how do we calculate VCE? Right, VCE, we are going to get it from the formula RC is equal to VCC minus VCE over IC. As a matter of fact, we do have all the other values. RC, we do have it. VCC, we do have it. IC, we do have it. We can then find VCE from there. That's our collector emitter voltage VCE, which is this one. So manipulating, of course, that formula there, multiplied by IC there, we end up having IC RC is equal to VCC minus VCE. So making VCE the subject, it means VCE therefore is equal to VCC plus IC RC. Therefore, we can now substitute the values directly. 20 plus IC 14 milli times 10 to the power of negative what? 3 multiply by RC. RC is 1 kilo. So that's 1 times 10 to the power of what? 10 to the power of 3. And that will definitely give us 34 volts. So there we are. That's marking our VCE. Let's go to the next question. The base current, that's IB, right? Where are we going to get IB? From the formula? IRB is equal to VCC minus VBE over IB. Right. That's what we are taking. We are taking this from the data sheet. With footnote enough we've been given. So we are simply saying IB, making it the subject, of course, cross multiply IB RB. That's much straightforward there. IB RB is equal to VCC minus VBE, right? So we can then make IB the subject. That will be IB, therefore, is equal to VCC minus VBE over RB. Hence, we can safely substitute other values that we do have. So we can say 20 minus 0.7, that's our VBE there, over right, RB we have been given, that's 800 times 10 to the power of what? 10 to the power of 3. And that will give us 2,413 times 10 to the power of negative 5 amperes. That's roughly 24.125 microamperes, right, using the EMG button there. Right, this is the value that we now end up having. Right, the beta gain, that's our next question. Right, beta is equal to IC over IB. Actually, it's a ratio between the collector current and the base current. So it is unitless as well. It doesn't have a value. So we can simply substitute that which we are having. 14 milliamperes, 14 times 10 to the power of negative 3, divided by 24 microamperes, which is 24,125 times 10 to the power of negative 6. And that will give us 580,31088, somewhere there. So roughly rounding off to 3 decimal places, that will give us 580,311 due to the instruction on the data or on the instruction sheet. So it's good to take note of that. So that's 580,311 without units. That's beta gain, doesn't have units. Let's quickly go. Question 3.3 reads, a supersonic radio has a fixed bias voltage with an input impedance of 1.169 kilo ohm and an output impedance of 1.96 kilo ohm. Calculate the values of the collector resistor and the base resistor with the precise method if the following information of the transistor is known. HIE equal to 1.2 kilo ohm, HOE 20 microamperes per volt, HRE is equal to 2 times 10 to the power of negative 4, and HFE equal to 6. RS is equal to 0. Now, let's start first with the collector resistor RC. How do we calculate? Because we are supposed to calculate these two, RC and then RB. Right, so we can get RC from the formula. The output impedance is equal to RC times Z2 over RC plus Z2, considering them as being parallel. So it means we need to calculate Z2. So Z2 is actually given by the formula. Since we are being asked to use the precise method, it means Z2 shall be given by 1 over HOE, right, minus HOE times HRE over HIE plus RS. This is the formula that we are supposed to use, right? So it means we have to first calculate Z2. So let us calculate Z2 first, right? So we are now calculating Z2. So Z2 therefore shall be given by 1 over, apparently we've been given HOE there. That's 20 times 10 to the power of negative 6, right? Minus HOE, that's 60, right? Multiplied by HRE, that's 2 times 10 to the power of negative 4 there, divided by HIE, that's 1.2, which means it's 1,2 times 10 to the power of 3, right? Plus 0, right? So if we punch this on the calculator, of course, it's going to give us 100,000. And that apparently is equal to 100 kilo ohm, right? That's our Z2. right? So now that we have our Z2, it means it's possible now to go and substitute into that formula Z0 output impedance is equal to RC Z2 over RC plus Z2, right? So let's substitute then Z0, the output impedance is equal to RC times Z2 over RC plus Z2, right? So we can directly put the values that we have. The output impedance, we have it, what is it? That's 1960 Y, was it's 1,96 10 to the power of 3, right? Is equal to 100 times 10 to the power of 3 multiplied by RC over RC plus 100 times 10 to the power of what? Of 3. We are simply substituting the values that we have in this formula. Remember, Z2, we have it. So it is the value that we are substituting. So if we multiply 100 times 10 to the power of 3 multiplied by RC, of course, we get this value 100 times 10 to the power of 3 RC. At cross multiply, it means we end up having 1960 multiplied by what? RC plus 100 times 10 to the power of 3 is equal to 100 times 10 to the power of 3 kilo. Remember, kilo is 10 to the power of 3 RC, right? So upon simplification, the bracket that we have created there, we end up having, of course, 1960 RC plus 1960 multiplied by 100 times 10 to the power of 3. That will give us 196,000 times 10 to the power of 3 is equal to 100 times 10 to the power of 3 RC, right? So this is what we are having, right? So variables to one side and constants to the other, it means we end up having 196,000 times 10 to the power of 3 is equal to, of course, what are we getting there? Having to simplify these variables on one side, this one and this one, they will obviously give us, after subtraction, 98040 RC. So it's kind of straightforward. 100,000 minus 1,960, we get 98,040 RC. So we now divide by that 98,040, divide by 98,040. That will give us, okay, so that's divide by 98,040. That will definitely give us RC being equal to, right, so what are we getting there? RC is equal to, right, right, punching this on the calculator, it's going to give us 1999.184 ohm, which is 1999.184 ohm. That is marking our RC. So we have answered that first part, which wanted us to calculate the collector resistance. All right. So now that we have it, let's go to the next question on calculating RB. Right. RB, we get it from the formula ZI, the input impedance that we've been given there, is equal to RB multiplied by Z1 over RB plus Z1. Fortunately enough, these formulas are given, they'll be there. They are there on the formula sheet. We are taking them from there. Right, but then we do not have Z1 there. So we need to calculate Z1 again. Right, so using the precise method, Z1 is going to be given by Z1 is equal to HIE minus HFE times HRE times ZL over 1 plus HOE times ZL. Okay, so that's our formula there. All right, so it means then we can substitute the values that we are having into this formula so that we calculate Z1. Right, so let us substitute HIE. We have it. What is it? That's 1,200. That's 1,2 times 10 to the power of 3 there. It's the same as 1,200, right? Minus 16, that's HFE, multiplied by 2 times 10 to the power of -4, right? Multiplied by ZL, and apparently that's at 1,999.184 that we've just calculated, right? Divided by 1 plus, right, HOE times ZL, that's a multiplication there, So we are saying that's 20 times 10 to the power of negative 6 multiplied by 9.184, right? So if we punch this on the calculator, that will give us 1176.934 ohms, right? That's marking our Z1. Now that we have Z1, we can then substitute into the formula Z2I, the input impedance is equal to this, right? So let us substitute. What are we getting? Zi is equal to RB times Zi is equal to RB times Z1 over RB plus Z1. So let us substitute 1,169 kilo ohm, that's 1,169, is equal to, right, RB is the one we are looking for, multiplying Z1, which is 176,934, is that 932? Sorry, on that error there. This is 932 actually, right? So that's 932 there. Right, so let us divide it by, that's RB. RB is going to give us, okay, that's the one we're looking for, plus 1176,932. Right, cross multiply again as we did with RC there. What are we getting? That's in 1169 bracket RB plus 1176,932, right? And is equal to 1176,932 RB. Okay, there we are. So multiply. So of course this will give us 1169 RB. Plus multiply 116 times 1,169 multiplied by 1,176.932. That will give us 1375822, which is 1,375,822.987 is equal to 117.932 RB there, right? Variables to one side, constants to the other. So this can be simplified. 1176.932 minus 1169.1169. That will give us 7.932 RB is equal to 137,582.987 there. So divide by 7.932. So we're just punching on the calculator 7.932. And then RB is obviously going to be what? RB therefore shall be equal to, we get 1,73452. That's apparently 173,452.217, which we can indicate as 173.452 kilo ohms. Right, that marks our answer for RB. So we have calculated as well RB as we have calculated RC, just like that. Right, so let's quickly go over to the next question. So our next question is question number 3. So question number 4, sorry. So question number 4 is saying, briefly explain the following terms with reference to operational amplifiers. The first one is the input offset voltage. So the input offset voltage, it is the necessary difference between the bias voltages at the input to obtain zero output voltage. That's an input offset voltage, right? Then 4.1.2, inverting input. Inverting input, it is the input terminal of a differential amplifier which produces an antiphase output when the signal is applied. So actually an antiphase output is also an out of phase output, right? Then 4.2.1, draw the circuit diagram of an inverting operational amplifier. So the circuit diagram obviously is going to be, right, there we are, of course, right, positive and negative, right. Let me try to enlarge this one so that my diagram is clear, right. So there we are, right, there we are, right, positive and negative. All right, then on the negative input, we now connect our feedback resistor, right, and then of course there is our output, right, and then of course this positive terminal is grounded, so let us ground it. There it is, right. So this is marking, so let's label it. That's R1 there, and then this is RF, the feedback resistor. That's V out there, the output. Of course, we have the V in on the other side. So this is marking the circuit diagram of an inverting operational amplifier. Let's go to 4.2.2. 4.2.2 is saying the input signal of an operational amplifier in the inverting mode is -2 volts and an input resistance of 15 kilo ohm. If the output voltage is 20 volts, calculate the feedback resistor. Right, let us first go to the V out itself. Is given by what? V out is given by negative RF over R1 multiplied by V in, remembering that it's an inverting amplifier. So due to that, it's obviously going to be negative. The V out, the output voltage has to be negative, right? So making R the subject there, the RF, because we are calculating the feedback resistor, mind you. So making it the subject, it means we can manipulate our formula. Okay, so that's negative RF times V in there, right? So making, okay, times V in. So making RF the subject, right? This negative, mind you, it is just there to indicate to us that it's an inverting operational amplifier. So in performing the calculations, we can actually negate it. It's still one and the same thing. Divide by V in, divide by V in. So RF, therefore, is equal to V out times R1 over V in. Hence, we can substitute the values that we have. 20 times 15 times 10 to the power of 3, which is 15,000, divided by 2. Right, so what do we get? Of course, we punch that on the calculator. It's going to give us 150,000, right, ohms, which is apparently 150 kilo ohms. That's our RF. We have our RF. Let's go to the next question. Question number 5. Question number 5 is saying, draw a neatly labeled block diagram of a general closed loop system. Briefly describe how the load, sorry, I skipped question number 5. Let me go in the great seconds, right? Saying what should be done with the unused or unutilized, apparently it's the same thing, unused inputs of a CMOS integrated circuit when it is connected to the circuit, right? They must actually be connected to the VDD or to the VSS. That's where they must be connected. Let's go to 5.2. Indicate whether the following statements are true or false by writing only true or false next to the question answer. Right? CMOS integrated circuits have lower noise input. That's false. It's false. They actually have high noise input. All right. CMOS integrated circuits are susceptible to static charges because of the low reactive input. That's actually false again. They can be damaged if subjected to high electrical fields, actually. Right. And in the next one, as soon as one works on the circuits of CMOS integrated circuits, the power supply to this circuit must be switched on. That's again false. On the contrary, switch off the power before you work on the circuit. It's a prerequisite. It's very, very important that we do so. Right? Electronic phase control. Let's go now to the question number 6. Draw a neat labeled block diagram of a general closed loop system and briefly describe how the load condition is kept constant. So we will have to draw it first quickly and bring it out. So I'm just... So here we have the reference input. Okay, just draw it quickly. Of course, right, then we go. Right, and then of course, here we have the SR again, the RC trigger circuit. Then we go to the load, right, and then of course, there is the feedback network. And lastly, of course, this is the display unit, giving back again to the comparator at this point, right. There is our diagram. There is our diagram, so we just label it quickly, right. We say this is the RC trigger circuit, right. This is the RC trigger circuit. Then this is the reference, right. This is the reference input. This is our reference input. Then we have the comparator at this point. There is the comparator. There is the comparator, right. There is the comparator, right. And then there is the error signal. We have the error signal at this point. You have the error signal, right. And then we have the SCR, the silicon controlled rectifier, yeah, SBG, right here. And then of course we have the load, and then we have the transducer. All right, we have the transducer, which is our feedback network. At this point, there is our feedback network at this point, right. And then we have our display unit. There is our display unit, right. And then we have our feedback signal. There is our feedback signal, right. Feedback signal. There comes out our diagram. So of course, this is the positive. That's our comparator there, right. That's our diagram. Then the question had said, with the aid of a diagram, explain the operation, right. The question was saying actually, display with the aid of a diagram, draw and briefly describe how the load condition is kept constant. That's what we had been asked to explain, right. So in description, number 1, we will say, right, in point form, of course, it's good to write that way. So you simply say, number 1, the comparator compares the feedback. So the comparator, which is this, it compares the feedback, right, this is the comparator. The comparator compares, simply it compares the feedback signal with the input reference signal, right. Then, as soon as the load deviates, it means changes, the feedback signal will differ from the reference input, and this difference is called the error signal. So what we are calling the error signal is that difference, and it is used by the control circuit to bring the load back to normal. That's the description we have to give, right. And then let's quickly go to question number 7. With the aid of a neat labeled block diagram, draw an instrument that displays the frequency of periodic electrical signal. Right. This is our diagram. So let's quickly draw with the aid of the block diagram. So I'm just going to draw it here quickly. Right, so this is how it comes out. So we are having, right, V1 at this point, right? We just draw it here quickly. Let me use this, right? There is the block diagram, right? And then we have right, and lastly, okay, there we go. That's how it's gonna come out. Right, all right. I'll just label it quickly. There we go. There we go. There we go. Right, number one, we start with there is our V1. We are saying this is the Schmidt trigger. So I will indicate it here. That's our Schmidt trigger. All right, and then of course, there we are. Right, of course, we go to the last part. Okay, let me just draw it nicely. So it's actually like this, right? Okay, right, there we go. And then we go to the counter, right? And then we go to the display unit. There we are, the display unit, right? And then we have the time base, generator, right? The time base generator. There we are, right? That's our diagram there, right? As a matter of fact, we are simply saying the Schmidt trigger there, it is there for the conversion of the analog signal input to the digital signal, right? So that's our diagram. And right, it just needed to be drawn and labeled as the way we have just labeled it. Right, let's quickly go to the next question. So we are now on question number 8. Question number 8, right, I will quickly go to that question number 8, and it says, right, if the total inductance of a Hartley tuned circuit is 10 millihenries and the oscillating frequency is 300 kilohertz, what is the value of the capacitor in the tuned circuit? Right. Okay, did I not skip a question there on question number 7? Apparently none. All right, I thought I had skipped something. Right, let's go to 8. Right, it was saying calculate what is the value of the capacitor in the tuned circuit. Right, we are gonna get our capacitor value from the formula FR, the frequency, is equal to 1 over 2 pi the root of LT times C. That's how we calculate the frequency in a Hartley tuned circuit, right? So making C the subject, first things first, we can just multiply by FR times 2 pi the root of LT times C is equal to 1, right? We can square now everything we can square. So of course, they will still get 1, but here we end up having 2 pi FR squared multiplied by LT times C is equal to 1. Then making C the subject, dividing by 2 pi FR squared times LT, divide by 2 pi FR squared, mind you, this is squared, times LT. So we end up having C is equal to 1 over 2 pi FR squared multiplied by LT, right? So we can now substitute the values that we have in this formula, remembering this is how we are calculating C. So let us substitute the values. 1 over 2 pi multiply by 300 times 10 to the power of 3, the one that we've been given, right, times 10 to the power of 3 bracket squared, right, multiplied by 10 times 10 to the power of negative 3, right, and that will give us 2,81477 times 10 to the power of negative 11. Pressing the ENG button, so of course that will give us 28,148 times 10 to the power of negative 12. That's apparently picofarad. So the capacitor is 28.148 picofarads. That becomes our value. Right, let's go to the next question. The next question is saying, briefly describe what happens as soon as the transmitter rotor moves through an angle theta. Briefly describe what happens when, as soon as that's question no, I'm at question 8.2. Draw a neat labeled circuit diagram of a 555 timer. That's our question there. Draw a neat label diagram of a 555 timer. So I will quickly draw it here on this space. So I will try to create the space to be a little bit bigger. Right. So this is our 555 timer. That's how it has to come out with its 8 pins. Right. So I will label the pins first. So there is 1. Of course, these are 5. There is 3. There is 4 and 8, and there is 7. So I will connect them now. Right. I have, so of course, the pin 4 is interconnected there. Together, they are now connected to the VCC, positive VCC. Right. And then there we go to the voltage divider resistors. There is R there connected to pin 7. Right, there is again, right, so I'll just I have to draw this one nicely. It's gonna come out like this. There we go. Right, so I will label that's RA there, and then that's RB there. Right, and of course connected to pin 6. Right, that's pin 6 there, again interconnected to pin 2. Right, and then it's grounded. It's connected to the earth. Right, and then pin 1 is also grounded. Right, actually that's the ground. Pin 1 is the ground. It is the one that is connected to the earth. Right, and then pin 5 must also be grounded, having been connected to a 0.01 microfarad capacitor. Then it's further grounded. Right, so there we go. Right, and then pin 3, it is marking the output. So this is our output. Right, and apparently that's our output there, and it produces the pulse to other circuits. Right, then we have the pin 2. Pin 2, it is it conveys a trigger to the bottom comparator. That's pin 2 there. And then we have pin 8 here at this point. It is actually the positive voltage supply pin connected to the source. And as a matter of fact, it must not exceed positive 18 volts, just out of interest. We may want to know that. Right, then of course, there we are. That's our square wave there. Right, so that's positive, and that marks T1, that marks T2. Then, of course, that's the sawtooth. Right. Then we can, that's 2/3 of VCC, and this is 1/3 of VCC. There we go. That marks our circuit. So, by the way, here there is a capacitor that must be connected at this point here. Right. That's a C there. There must be a capacitor there. Right, there is our diagram. That's our 555 timer with its 8 pins. It's always having those 8 pins. Right, so that's how it has to come out. Let's quickly go to 8.3. 8.3, it's saying calculate the oscillation frequency of an astable 555 timer with the following values RA, RB, and C having been given 90 kilo ohm, 60 kilo ohm, and 1 microfarad there respectively. So the question is saying the oscillation frequency. So directly I will calculate that F0, the oscillation frequency, is equal to 1.443 over RA plus 2, right? That plus 2 times RB multiplied by C. That's our formula there for the oscillation frequency. So let us substitute what we have. 1.443 divided by 90 times 10 to the power of 3, of course, plus 2 times 60 times 10 to the power of 3 multiply by 1, okay, multiply by 1 times 10 to the power of negative 6. And what will that give us? That will give us 6.871 hertz. That marks our oscillation frequency. Let's go to the next question. It's saying, name 2 factors that may destabilize the frequency of an oscillator. There are various number of factors that may destabilize the frequency of an oscillator. Number 1, power supply, that is the change in DC direct current. Then the output load, the change in the output load can also destabilize the frequency of the oscillator. And then the temperature variations, the changes in temperature, and then of course the operating point. Those can affect or can destabilize the frequency of an oscillator. That oscillation frequency we have just calculated there. And let's go to question number 9. Question number 9, it's saying draw a neat labeled circuit diagram of a closed loop system in which synchronous motors are used to control the radar antenna, the radar antenna, right? Okay, so there we go. Okay, so we have a winding here. It goes up, then I have another one. I have a winding also this side. It goes down. Okay, okay, so then all right, there we go. Right, there is a signal. Right, and then we come to this side. Right, and then here another winding. It goes down. This one coming this side, and they're connected to another. Right, there we go. There we go. Right. Directly connected to this. Right, there we go. And then of course, right, and then we have our amplifier. The two are connected to the amplifier. Right, there is our amplifier. Right, and then we now go to the motor. There is a motor right at this point, and I'm going to indicate it here. Right, just this part. All right. Right, and then the two now connect it, right, and then we go up, right, okay, right, there we go. Okay, just this part, all right, and then, all right, there we indicate our antenna, all right, there we go. Currently, it has to be right, and then it's directly connected, right, and then you can label it now as 2. You can label it, right, X is here, and then this is TX. It's our transmitter and the receiver, right? That's S3, S2, S1, and the same thing, that's S2, S1, and then actually this has to be connected, right? Let me try to write. There we go. Right, there we are. Right, it has to be right. There we are. The last winding for S3. It's here. Right, pardon my diagram just here. It's a little bit poor, but let me just try to bring it out nicely. Right, so I'll pull this one a little bit down, just quickly. Right, there it goes, right, to my amplifier. Then, of course, this one will go straight now. I think now it's a little bit smart, right, just like that. Right, there we are. Then the last part of the winding connected straight to our S3. That's our S3 there. And then, of course, we have our amplifier. That's our amplifier there. Right, and then, of course, we say it is connected directly to the motor. Right, there it is to the motor. Right, we label the motor here. So we say that's an amplifier there, that's R1, that's R2. Right, and then we have our radar antenna right at this point. Right, there is our diagram. We are answering the question number 9.1.1. Right, and then 9.1.2, briefly describe what happens as soon as the transmitter rotor moves through the angle theta. So we are now explaining what will happen. So number one, the transmitter TX and the receiver RX are in balance as soon as the rotors stand at the same angle. If the rotor of the transmitter turns at an angle theta, the rotor of the receiver will produce an error signal to turn the motor. Right? That's exactly what happens. And then the antenna also turns the rotor of the receiver at the same angle theta so that the error signal becomes 0. Right? That's what basically happens. Then the next question, 9.2, draw a neat labeled circuit diagram of a precision switch in which a light-dependent resistor and an operational amplifier are used. Right, so we want to also quickly draw that one. Right, so I'll start at this point, right, then we have our light dependent resistor with here, right, there it is. All right, and then That's our LDR there, so I'll just label them. Once I'm done, then I'll ground it right at this point. Right, then we go the max resistor R1. Right, it's also connected right there, marks our operational amplifier. Right, and then the negative, the positive, right, and then it's connected directly resistor R2. Right, so this is marking resistor R1, that's P, right, and R2, right, these are 10 kilo ohm resistors. They are forming a voltage divider, 10 kilo ohm, and also 10 kilo ohm here, right, and from there, say this is positive and negative, right, and then there we are. Right, and then this is grounded as much as this one is. Right, there we are. Pardon me, it's a little bit poor. It has to be right. There we are. So is this one also grounded? Right, and then go to our output. It forms the resistor there, and then of course we have another resistor right at this point. Right. That's R4 there. We are labeling it R4. We are labeling this one R3. Now we go to our transistor. Right. That's our PNP. Okay, there we are. Okay. Right. Forming our positive 12 volts right at this point. Right, and then we go down, right? First things, we have the diode here. There is our diode D1, right, grounded. Then there we are, right, grounded again, right at this point, right, and then our switch right at this point, right, then to control circuit, there we go. This is marking now the control circuit, to control circuit, right, and then of course at this point, right, we indicate an interconnection, right, there we are. That marks our circuit diagram having been labeled. There we are. R3, it's 1 kilo ohm, and also R4, 1 kilo ohm. They are also forming a voltage divider for the transistor. So we are saying R1 and R2 form a voltage divider which produces a reference voltage to the operational comparator. That's what is happening there. And then P is a precision potentiometer, this P that we are having, right? This is our circuit diagram. We have answered the question, right? This is marking the end of our revision, right?